Today, I'm going to give the lecture, which might be the most important one for everything about epidemiology. So please pay full attention today. And the topic is causal inferences, bias, confounding, and interaction. The most important thing is about confounding, which is one kind of bias, but it's the most important one. How we do the causal inferences and the role of confounding in the whole consideration of the causal relationship in a hypothesis. In interaction is a similar but different phenomenon compared to confounding. So I just highlight it for the purpose of help you have a better understanding about the differences between confounding and interaction. So, and this is my favorite part about epidemiology. So it's very exciting. I can tell you that epidemiologists takes like at least 70% or to 80% of efforts to deal with the confounding every single day. So we've been struggling about confounding almost every day. I will try to apply 3 different kind of ways to help you understanding what the confounding is, which is not available in any textbook. First of all, I will raise a question about eternal question to ask, why people get sick. I'll talk about the journey from association to causation. No matter biostatistics or epidemiology, what we can do will be mostly the association for the exposure to the outcome. But it's hardly to be something about the direct causation or causal relationship. No matter for epidemiology or biostatistics, we're just providing the tools to establish association. But it will be still very helpful for us to establish the causation step by step. Okay. Then we'll go into how to infer a causation, or so-called causal inferences. There are some guidelines to be followed for the judgment of a causal relationship. And then I'm going to introduce the different types of biases. And the most important one is the confounding. So I'll spend a lot of time on elucidating confounding, what it is all about, why it is so important in epidemiology and all the other human subject studies. And then I'm going to introduce the similar phenomenon called effect modification or interaction, which is similar but totally different. But it'll be important to know the differences between confounding and effect modification. So that's why I put them together. Okay. An internal question to ask. Since the birth of a human being as a race, we'll keep on asking ourselves about why people get sick. And for a long, long time, we might be able to identify some risk factors. In other words, some characteristic in the population might increase the risk of the disease by observation. Or maybe nowadays we'll be able to identify the risk factors by some other medical or molecular biological way to identify the risk factors and make sure the role of the risk factors contributing to the progress or pathogenesis of disease. And also we find out that some factors might be able to prevent people from getting the disease. Okay? So from what we learned for relative risk about the consideration of exposure to outcome, risk factor will make the relative risk higher than 1, much higher than 1. Okay? And risk factor will make it lower than 1 because we use the indicator of relative risk for the estimation of the impact of these factors. So relative risk is a risk factor to put people at a higher risk, or it's a factor to prevent people from the disease by higher than 1 or lower than 1. Also, we find out some factors might be important somehow. It doesn't matter. In the relationship, in the consideration of relationship from these factors to the outcome of the disease. Okay? So it could be effect modifier. I'm going to tell you why in today's lecture. So we are trying to generate the association. I have to emphasize the role of epidemiology. It's part of etiology, which is used to understand the cause of diseases at the population level. Of course, etiology could be something as small like a molecular level or organ level, tissue level, about why people get sick. But epidemiology is about population level. But for most of the chance, epidemiologists can only do the observation on humans as populations because there are a lot of considerations. We cannot manipulate the exposure on population. I can request you smoke for 20 years and you don't smoke, and I'll wait to see what happened for 20 years. It's not possible. So what we can do about the exposure which might be harmful to humans' health is to observe what's going on among this group of people. So mostly what we can do is observation. But with only observation, what we can find is just association. So epidemiology and biostatistics are essential tools for us to identify the association, but it's not totally or exactly equal to causality. It's very hard to make sure that with a single study. They are still important. And biostatistics only help us to make the decision at, for example, clinical decision, or make the conclusion for a single study at a standard stage of the research. But it's not the causal relationship itself at all. It's just a probe to help us to identify they might be associated to each other somehow. But it cannot help us to judge the causal relationship. So biological sense is essential. It's very easy to find the statistical significance for among the variables available in a research or data set. But biological sense is still very important for us to establish or generate a hypothesis which makes sense in molecular biology. Okay, it's just like a treasure map to help you to dig out the treasure in a treasure island, right? You cannot dig around to find the treasure. It will be too much effort to spend. Okay, then people might ask, for scientific research, what is the first step to do? The first thing is to yield a hypothesis, and it has to be something answerable. It could be something based on from clinical impression. Clinician tell me that she found that people with dementia will be more likely to have the history of depression. So is it true that depression is a risk factor for dementia? Or dementia or the symptom of dementia is just an early symptom of dementia? Okay, depression might be an early stage or early sign of the development of the dementia. So but still under debate for argument for a long, long time. For a lot of chances, the hypothesis could be generated from clinical impression like that. Or it could be something from the descriptive epidemiology. The information about person, the characteristic of person, like demographic, socioeconomic risk factors, or time and place clustering with the data available. Like what John Snow did. He just put the distribution of the cases on the map to generate a hypothesis that the occurrence of cholera might be related to water supply, right? That's what he hypothesized. And then he tried to find evidence to answer such a question. So it's based on descriptive epidemiology. Or it could be something from ecological study, which is a study design used to focus on group characteristics, no matter for exposure or outcome, like the water supply coverage and to the neonatal mortality, for example. So both of exposure and outcome are given at the group level, then so-called ecological study. Or the example I raised last time, that chocolate consumption is related to the Nobel Prize, the number of Nobel Prize winners. It's also an example for ecological study. Or it could be something based on the previous analytical study, like case control study, cohort study, and even randomized control trial. For this kind of study design, we focus on individual characteristics. So with those individual characteristics, we'll be able to consider the relationship for exposure to the outcome at the population level, and also consider the issue or adjust for confounding. And it could feedback to generate new hypotheses, and it could perform further studies by these analytical studies in epidemiology. So let's move back to the causal model suggested by the ancient not really ancient, scientists or experts in the field of epidemiology long time ago. The first one, the simple one, which is so-called epidemiological triangle, suggested by Chang. In the past, most of the epidemiological study were about infectious disease. So his idea is to emphasize the interaction between the host, the patient or population, and the agent and the environment. The occurrence of diseases is something caused by the interaction with the three components. So this is a simple but pretty useful for us to understand what's going on for the roles of these three components to make people sick. So it emphasizes the interaction between these factors. But it would be more applicable in infectious diseases only. Because nowadays a lot of study might not have so-called agent. Okay, so this is the simplest disease model. Okay, and also someone called McMahon suggests a more complicated disease model called web of causation. So here's an example about the causation of myocardial infarction. This could be very complicated. So the endpoint is a myocardial infarction. And there are a lot of different risk factors. And for example, social pressure might cause the diary excesses and then cause diabetes and then increase the, or also hyperlipidemia, hypertension, and then eventually cause coronary occlusion and eventually cause myocardial infarction. Or it could go through the other different causal pathways to make people sick. So this is the other extreme, the most complicated theory about why people get sick. But it might be useful for us to consider such kind of chronic disease with very complex mechanism for the pathogenesis. It could be biological, psychosocial, or the development of the industrial society. And the third one is so-called the wheel, suggested by Mosman, who's also a master in the field of epidemiology. He emphasized the idea that the host is at the center for the disease model with the specific genetic characteristics which differ from person to person, right? And people were surrounded by biological environment, the social environment, and the physical environment. So that's how people get sick. And that's how we have to consider the whole thing, that there might be some interaction between the host, the biological environment, the social environment, and the physical environment. So it's another alternative way to help us to understand. But this kind of model emphasizes the interaction between human beings to the environments, especially for gene-environment interactions, right? But personally, I think this one is the one which makes most sense for me. Dr. Rothman, he's still alive, he's not ancient, but he suggests that we could consider the whole thing about why people get sick in this way. Let's call it a pie, A, B, C, D, E. It's just a pie to make people getting sick. Okay, and every risk factor like A, B, or C, or D is one of the contributing factors. Okay. But in the consideration of chronic disease, generally speaking, there's no single factor. It's multiple. Okay, so every single one is one of the contributing factors. But once you have all the risk factors in one pie, then it just becomes sufficient to cause the disease. So it's a risk factor set to make people sick. So this is a sufficient combination of the risk factor sets. Okay, and people could get sick by the other sets or these sets. Okay, no matter it's set 1, set 2, set 3, they serve as a sufficient risk factor set. And if you pay attention to the combination of these different sets, you will find that the factor A is here, here, and here. So A sounds like a necessary one to cause the disease, right? Like an early stage gene mutation for lung cancer, for example. So A will be something essential, no matter how you get incident lung cancer. So A is a necessary one. Okay? So this will be very helpful for us to understand how people get sick with the multiple risk factors, especially useful for the study about chronic diseases nowadays. So it makes more sense to me. And this will be very helpful for us to understand what is so-called confounding and what is so-called effect modifier later. So I'll come back to this kind of the causal models or disease model later. Okay. And then let me introduce the types of association. Statistical association is simply defined as p less than 0.05, right? But it could be something non-causal because of secondary relation. I will show you what is so-called secondary relation. But even if it's causal, it could be direct relation or indirect relation. But no matter how, causal relation is always better than non-causal relation, because correlation will be very, very helpful for us to deal with the disease or manage the disease. To cut the correlationship, then we could stop the development of the disease in the progress. Okay? But if it's non-causal, it will show statistical significance, but it doesn't help for us to stop the development of the disease. Okay? So although we can see statistical significance, but non-causal relation doesn't help. Okay? So what we want to know is correlation. So that's why we need to use statistical methods to help us to identify the association, to help us to do the judgment. Okay. And epidemiology also take a very important role, because a good study design will be essential to generate useful statistical information for the purpose of statistical analysis. Okay, so both of them are essential. I mean, epidemiology and biostatistics is very helpful for us to identify the causal relation, but it's only shown with statistical significance for association. What is so-called secondary relation? If A to B is a correlation, so you could find the statistical significance. Okay, so this is the nature that A cause B, and also A cause C with a causal relation. Okay, but B and C might not be causal, but statistically it will show statistical significance for between B and C. So we call it secondary relation. Significant but not causal, so it's not very helpful. So even if we try to do something to block the relation B to C, because it's not helpful for us to prevent the disease. Okay, but what about indirect relations? A to B is direct causality, and B to C is also direct causal relation. Then A to C will be indirect relation, indirect causal relation. So this is good. So we could try to modify or change B to stop the progress of the disease or the causal pathway from A to C. So indirect relationship is still useful for us to stop the progress of the disease. And also it will show statistical significance, right? Okay, so this should be pretty straightforward. Then how? How can we use the what we learned up to now to help us to do the judgment of a causal relation, or give us some guidelines for us for the judgment? The first one is the temporal relation. In other words, the causes always happen before the results. This is very intuitive and straightforward, right? Before the invention of time machine, this will be always true. So the risk factors should be pre-existing by the onset of disease. If not, then it cannot be a risk factor or not the cause of the disease. But sometimes it's very difficult to find out or clarify that it happened before that, the exposure before the outcome, because the induction or latency period could be very, very long. You might lose the information about exposure, or you lost the chance to identify the outcome because it's too long, or it's too short. It could be something like an accident using a mobile phone to the accident. The period might be very, very short, in seconds, or even less than 1 second. So it might be hard to identify which happened first. Okay, so accident is an example for a very short induction or latency period. And cancer and smoking will be example for very long, but sometimes not easy. But this is the only necessary one for the judgment of a causal relation. The others might not be necessary, but this is definitely. And the second one is about the strength of the association. You might ask me what is so-called the strength. In epidemiology is the relative risk or impact of the risk factor. Okay? So in other words, if we have a very, very gigantic relative risk, there will be more likely to be a causal relation. So the bigger the relative risk, the more possible to be causal. So if we can identify dose response effect, in other words, if the exposure is higher and higher and risk is also higher and higher, there'll be more likely to be a causal relationship. But you have to pay attention to the pattern of exposure. Sometimes it only happens in a specific pattern to make it effective. Like what I said, the example I raised for the exposure to some exposure which is related to seasonal change. Okay. And the other thing is that sometimes the dose response effect might not be so true because there's a threshold effect. So in other words, it's the so. So in other words, along with the increase of exposure, it starts to affect it beyond a specific point. That's the nature of the causal relationship. Then you might not be able to identify the dose response effect. It's not do, re, mi, fa, sol. Not so straightforward. The other extreme is radiation, the effect of radiation to cancer or acute damage because of the radiation. There's no threshold effect. So it's from 0 to extremely high. So it's a perfect example for a dose response effect. The third one is replication, or we can say it's about the consistency of the association. In other words, if something is real, it's causal, there's more likely to find the same thing at different places, in different medical settings, at different populations, at different countries. Okay. So you can replicate the results everywhere, on human being, of course. They'll be more likely to be causal. But it's possible that people just make a mistake in the same way all the time, right? Okay, but we'll talk about it later. Consistency reduces the chance of type 1 error, which is the essential evil in biostatistics, right? Like the alpha level has been set as 0.05, so it's so-called type 1 error. So in other words, even if there's no relationship at all, we have 5% of the chance to make the mistake, to say that, to make the conclusion they are statistically significant. But actually there's no relationship, no association at all. So it just simply happened by chance. That's why we call it essential evil. Okay. But it's also possible that people just do the research in a consistently wrong way or systematical mistakes. So it's also possible that it's replicable, but it's not causal relation. But in epidemiology, it's critical or crucial. If we could find the outcome or the relationship replicated at different places, there'll be more and more likely to be causal. Smoking is a good example. We find exactly the same thing, the relationship between smoking to cancer, everywhere in the world, no matter the country, ethnicity, blah, blah, blah. Because what we can get for a single epidemiological study is just a sample. So every sample or every study, you have 5% of the possibility to have the type 1 error, right? So it's very unlikely that it happened again and again and again at different places, right? Then the chance of that every study was wrong is very limited. If you repeat the research at different places. So with multiple studies, the cumulative type 1 error will be lower and lower. Okay, so that's why in epidemiology, sometimes we perform the meta-analysis. If there's been multiple studies on the same topic published, then we perform a meta-analysis to summarize the research outcome together to minimize the issue of type 1 error. So it's about replication. And the other thing is biological plausibility, which is very important. Biological plausibility means that it's reasonable in terms of biology or molecular medicine. So if we can find something which is coherent with the existing information from biological knowledge, then that'll be good. But sometimes we have no idea about the biological mechanism of the disease, but we can still make the conclusion that it's causal. The best example is that Jon Snow. He suggested and he tried to find the evidence about the relationship between the exposure to something in the water supply to the risk of cholera, right? But at that time, human beings have no idea that the cause of cholera is because of bacteria. So we have no idea about the biological mechanism for cholera at all. But in epidemiology, he generated sufficient evidence to prove that it's causal. Exposure to something in the water is a risk of the cholera. So it's not necessary for controlling epidemiological diseases like cholera and Jon Snow. It just simply suggests to avoid using the public water supply with a pump at the square. And then you could get rid of the threat of cholera. Or you could do something to boil the water or something, then you could avoid the cholera. But it's not necessary to understand the biological mechanism behind it. Sometimes you could find the conflicting epi findings because there could be some other social cycle issues, implement of health services or unknown reasons. So that's why we might find conflict information on the biological plausibility. Do you know that one of the examples is that do you know why the smoking rate is always higher for men compared to women everywhere in the world? Why is it always higher for? So men are vulnerable. Yeah, it's more about social. We cannot find any biological evidence about it. There's nothing weird going on our Y chromosome to make men more likely to be addicted to cigarettes, right? Yeah, it must be some kind of social cycle issues. And there are some other minor ones, like specificity of the association. If some kind of exposure is very specific, not available anywhere in the world, but also to find a very specific disease only happen among the people who are potentially exposed to such kind of the exposure, then it's more likely to be a causal relation. So it's a so-called one-to-one relation, like asbestos exposure as a risk factor for mesothelioma, which is very rare but specific kind of the cancer. And we could only find it happen on people exposed to asbestos. So it's a one-to-one relationship. So it's easy to find out the correlationship between asbestos exposure to mesothelioma. But it might not be very helpful because it does not work for multifactorial etiology, like cancer is a good example. We have known that smoking is one of the major risk factors for cancer, right? But you could also find someone who has been smoked for 60 or even 80 years, but still free from cancer, right? Yeah. So it's not one-to-one relationship. So if it exists, that'd be great. If it doesn't, it's not necessarily wrong for the judgment of causal relationship. The next minor one is called consideration of alternative explanations. The example is confounding. For example, the number of teeth and the dementia. If you try to find the information or count the number of teeth in a group of people, and then also try to screen or do the diagnosis of dementia among this group of people, you might find a very strong statistical correlation, p less than 0.00005. Okay? But is it causal? Not really. Yeah, because they might have something going on among the group of people with different number of teeth, right? So age would be something we have to consider because older people will be more likely to lose their teeth. Okay, and age is also definitely a risk factor for dementia, right? So without the consideration of age as a confounder, you cannot make such a conclusion at all. So if you try to sort it out by different kind of methods to deal with the confounding from age, you will find that the relationship might not be so strong, or even there's no relationship in terms of statistics. Okay, so this is alternative explanation. Age is alternative explanation about the relationship between a number of teeth and dementia. So this is an example. Or cessation of exposure. You could stop the exposure or block the exposure of something and the disease disappear. Then will be another way to help us to judge the correlationship. Again, but if the incubation period is very long, then it might not be very helpful. Right? If you start smoking, then maybe you could only observe the decreased risk of cancer after 10 years or 20 years. So it might not be very helpful again. Okay. But here, why I call the confounding is a minor one, but I emphasize it's very important in epidemiology. That's because confounding is everywhere. It's very common in almost every single epidemiological study. So that's why I say it's very important. It's very useful, or it's essential to control the confounders before you can make any conclusion. This is another one, but it's an essential one. It's a very common one. Without doing it, we cannot make the conclusion at all. So it's kind of a must in every single epidemiological study. We have to do something to deal with it. We call it confounding control. And the other issue is about the measurement, the accuracy of measurement in epidemiology. First of all, I have to tell you that all science are about measurement. Even if you just watch the star, it's kind of measurement. You might find out that the star might move in two major different kind of ways. A group of the stars just fixed there all the time. The other group of stars just move in this way all the time because they are planets surrounding the sun. They are not a regular star like the sun in the sky. So even if we just observe what's going on for the movement of the stars, it's about measurement based on the observation. So in epidemiology, we have to measure the exposure and the outcomes to find out the effect of the exposure to the incidence of disease. That's the basic activities in epidemiology. So it's important to keep the accuracy. There are some indicators about the accuracy of epidemiology. The first one is validity, which is about the precision of the true value, or it's about reliability, which is about the reproducibility with similar settings. But you don't need to worry about it. I will spend 2 hours about the validity and reliability in a lecture about screening in the following lectures. So the best scenario is the high validity and high reliability. Then we are happy about it. But the worst scenario is not low validity and low reliability. Because if we have both low for validity and reliability, we just inconclusive. We cannot make the conclusion at that stage. But if we have high reliability but low validity, that's the worst scenario because we will make a wrong conclusion. Then we'll take a wrong action against the disease. So spend a lot of money and efforts, but end up it doesn't work. Or even you could do something bad for your intervention. But don't worry too much at this stage. Okay. Bias is simply defined as the loss of validity. So it's something, it's any systematic error in the design, conduct, or analysis of a study that results in a mistaken estimate of an exposure's effect on the risk of disease. But I don't need to remember this kind of thing. Or selection bias is exposure, blah, blah, blah. Anyway, I'll come back to selection bias. I'll spend a lot of time on it in the lectures in the following weeks. So you don't need to worry too much. But you have to realize that selective means the sample is recruited depending on some characteristics which are related to exposure level and also the outcome. Then that's selective. But how it would cause selection bias, I will give you more information about it. The example is a hospital-based study or selective non-response. There are the very typical examples about it. And the other thing is so-called information bias. In core studies, it could be the information collection about exposure or diagnosis affected by the characterization of the exposure status. Okay, that's information. Because the outcome or the exposure is because of the exposure status to cause such kind of the bias. This is so-called information bias. So in randomized control trial, we apply the method called blindness to eliminate the issue of the information bias. Okay, but in case control study, it's simply the information about the exposure affected by diagnosis of disease, or so-called misclassification. And recall bias is something important, which is one of the information biases. And finally, we will start with my favorite part in epidemiology, confounding. Let's first consider the relationship between a risk factor A and a disease B, which has been specified in your hypothesis. What is a hypothesis? It's simply a causal relationship. The exposure of something is related to something, and they have a causal relationship, okay? Which is different from the null hypothesis in biostatistics. We assume there's no relationship, right? There's no, we call the null hypothesis, and then we do this and that to reject the null hypothesis, right? But in epidemiology, it's more straightforward. Something is the cause of something. A is the cause of B. That's it. Okay? This is the epidemiological research hypothesis. Then, another independent real risk factor, X. In other textbook, it's just another risk factor. Let me tell you, it has to be a real risk factor. In other words, we are pretty sure about it, the mechanism of it. It's a well-known, well-characterized risk factor for the disease B. So now, the real risk factor X, considered within the relationship of A to B, is the third-party factor. It has to be an independent risk factor. The third step, since X is a real risk factor, so it must be related to the disease B, of course, right? Because we know it. X to B is causal. We're pretty sure about it. So it must be related. But if X works through another biological causal pathway, then it's a potential confounder. Not a sure thing as a confirmed confounder yet. But finally, X could be considered as a confounder within the relationship of A to B. Okay, this is a relationship we want to consider in my hypothesis, right? And X is something already known. Okay, that's the scenario for the consideration of confounding. So the last step is that the final trigger is that if X is correlated to A by chance or by any other reason, then it's a confounder. With the example of gender and smoking, it's not happened by chance, right? And it's not biological either. Men are more likely to be a smoker, right? So it could be by chance, or could be some other psychosocial reasons to make the X related to A, or smoking related to gender related to smoking. Then X is a confounder. Okay, so now you understand the story, right? Okay, but if we look into the scenario about how to judge confounding, let me give you some insights. So we consider one relationship A to B at a time because epidemiologists are simple-minded. We are very straightforward and focused. So that it's only one relationship at one time. So in other words, in one hypothesis, you only specify exposure to one outcome. So if we want to do more, then they are independent to each other. Different kind of hypothesis, you have to consider the whole thing about confounding independently. You cannot apply everything in the same way. And the independence here for another real factor X means biological independence. So independence means that it's just biological independence, not only statistical independence. And the correlation between A and X is merely statistically or by chance. Or it could just because of some other psychosocial reason. But if X is involved in the causal pathway from A to B, that's surely not a potential confounder because it's not biologically independent anymore, right? So it's not possibly as a confounder. But potentially it would be possible for effect modifier. So don't worry about that. I'm going to talk about it later. So you have to make sure that X is not involved in the causal pathway from A to B. We call it a mediator, right? And the bias of confounding is very, very common in epi study, almost everywhere. So that's why we have to deal with it. Although in terms of the theory, it's just a minor one, but it happens everywhere for every single epidemiological study. We have to try our best to deal with it before we can make any conclusion. There are many ways of the confounding control has been suggested. At the stage of study design, we could do subject restriction. So if X is something, a potential confounder, we could simply to do the comparison for the people without the issue of X. So if gender is a potential confounder, we just restrict the analysis in men only or in females only, then gender is not a confounder anymore. But if we do this, we'll lose the information about a specific gender, right? Okay. The other thing is the matching, or so-called partial restriction. So if we are in our exposed group, the gender distribution is like this, and we just try to do the individual matching, for example. So we have one male, you get the other male in the comparison group. One female, we find the other female in the comparison group, 1 to 1. This is called individual matching. Then in the end, the gender structure will be exactly the same between the comparison groups. We could do exactly the same thing for age structure. We have someone at age 20, we find the other age 20 here. For case control or exposed, non-exposed groups. This is so-called matching. Or we could do randomization. If we could manipulate exposure by the study design of a randomized controlled trial, like the development of a new medicine, that's the only way to perform such a kind of study. So we just assign people in different groups randomly, and one group is the so-called intervention group. So we give them the exposure of the medication, the intervention. And the other group, we just give them the placebo. Okay? And because of the process of randomization, theoretically, the distribution of those contributing risk factors will be even or the same, similar at least, similar to each other. This is called randomization. So we are going to talk about it in the randomized controlled trial, so don't worry too much at this stage. Okay, so at the stage of data analysis, there are a lot of things we can do, like a standardization, especially for age structure. So we have to learn it, especially in the data analysis for cohort study. Or we could do stratification with the Mantel-Hansel method to do the adjustment for the stratified factor as a potential confounder. You just need to know the name of it. Or lastly, we could use the mathematical modeling. You've learned something from Andre about it, right? Logistic regression, linear regression. Why we need to use multivariable analysis or multivariable modeling methods. That's for the purpose of confounding control. Okay, and there's mathematical modeling. So you might need to use a computer, or you might not be able to make it down by paper and a pencil. And the other thing is about effect modifier, or so-called interaction. This is a similar but totally different phenomenon. So that's why I have to talk about it, to make sure that you do understand the differences between confounding, which is a bias, which is something wrong, which will make you make a wrong conclusion. But effect modifier or interaction is different story. Okay. So now let's consider the relationship between A and B again. It's something specified in our hypothesis for the exposure of A to the disease of B. And another risk factor X is considered within the relationship. This is similar up to here. But X is involved in the causal pathway. So it's indirect, A to X, X to B. So it's not necessarily biological. It could be something psychosocial. And also it could change the effect of A to B dramatically. Then that's effect modifier. That's why we call it effect modifier, right? It cannot be controlled because that's the fact That's the mechanism behind it. That's the biological, part of the biological mechanism for the correlation between A to B. So we cannot control it. It's not a bias. There's nothing wrong with it. It's just basically the nature about the relationship between A to B. Okay? So what you can do is to explore it, explain it, rather than control it. It's not a bias at all. So it's also a third-party risk factor issue, but it's not a bias. Then we could do stratification or interaction terms in the modeling to explore the role of the X in the consideration of relationship from A to B. Insight into interaction. The phenomenon of interaction is rare in epidemiology. It's not like confounding. It's everywhere in any epidemiological research. But effect modification is relatively much rarer. And theoretically or generally, there are some underlying biological mechanisms inside, like Rothman's causal model. I'm going to explain it by the Rothman causal model later. So since it's not a bias, it's not something wrong, we don't need to adjust it or control it. But we have to report the results by stratification. If X exists, it's like that. If the X does not exist, it's the totally different story. That's effect modifier, right? It's pretty straightforward. So we just report the results or explore the relationship or the story. A variable can have the potential to be both effect modifier and confounder. So sometimes we consider effect as a effect modifier, and we also consider as a confounder. I know there's some kind of conflicting theoretically, but it happened. Just the factor X just play different kind of roles in different analyses. So there are two different third-party methods about the relation between a cause and the results. Let's go back to the causal model suggested by Rothman. So A, B, C, D, and E constructs a sufficient risk factor set. So people get sick if they collect everything here. So A is a well-known risk factor because we know it contributes in different kind of ways to cause the same disease. So now, if you want to perform research about the effect of E, which is new, that's why we generate a new hypothesis to perform such a research, right? Or H. Then we have to consider A as a potential confounder because we are not sure that, we have to make sure that the distribution of the factor A is the same in the comparison groups. If not, then A will be an issue. It will be something to be challenged by the others. A so-called alternative explanation for the relationship we identified, or wrong estimation of relative risks. Okay, that's for confounding, right? But what about effect modifier? So sometimes people could have ABCD, E, and the other group of people might get sick because he or she got A, B, F, G, H, or he or she might have A, C, F, I, J. So it's just open a different kind of channel, different causal pathway to make people sick. That's the phenomenon of the effect modifier. Okay, that's why the risk change dramatically because they go through different causal pathway. Okay, so this is the second way to help you to understand confounding and interaction. Okay. Third way, so I have the three. In the very beginning, I told you that I have three different kind of ways, alternative ways to help you to understand interaction and confounding, right? Okay, this is the third way to understand what is so-called confounding and what is so-called effect modifier. So let's consider exposure of H as a risk factor for lung cancer, for example. Let's simplify the story that so there are only two groups of H, younger than 45 or older than 45. And then we try to get the information about the gender of those people, younger or older. Okay, and find out that there's no differences between men and women. So gender is not a risk factor, right? Because it makes no differences. And it's not a confounder. Okay. But what if the story is like this? The incidence for female is always higher than male, and we know it. It's everywhere. We observe it in different kinds of studies. So we're pretty sure that gender is an important risk factor to make people sick for lung cancer. And then it's a potential confounder in this scenario. But it's not a confounder yet, unless the distribution of gender is different between the different age groups, which is considered as a major exposure interest in your hypothesis. Then gender becomes a sure confounder. And what if the scenario is like this? If for younger age group, the incidence of lung cancer is higher for men, but in the older age group, the incidence is higher for women, so it's like this cross. Then it's an effect modifier. In other words, the effect of the age could be modified by gender. So gender is an effect modifier here. But it's not a bias. That's the nature of the disease. Then we'll have a better idea about what happened between different genders. Maybe for men, it's more about cumulative exposure to the environment factors, air pollution, smoking, blah, blah, blah. And for women, it might be about menopause, for example. So there might be some factors about hormone level change the effect of the age to the incidence of lung cancer. So with the knowledge about effect modifier, we'll be able to provide or give us some hint about the underlying biological mechanism. But for confounding, it's just simply the effect of the non-independent risk factor. It's just simply the distribution of the non-risk factor is different in the comparison groups. So we need to deal with it because it will provide a misleading estimation of the relative risk. Okay, so the figure will be very helpful for you to understand what is so-called confounding and effect modifier. Okay, personal insight is a long way from association to causal relationship. But when we are trying to perform a new study in the very beginning, what we can find is just association. We might be able to find information or the association at the population level, and maybe in the future we'll be able to find out what happened at the molecular level or tissue level or organ level. That's what happened in John Snow's story, right? He just found the association or the evidence at the population level, and then eventually find out it's just simply caused by the bacteria in the water. It's a long way. And up to now, there are still a lot of things that we only observe the association, but we cannot find the correlationship at all. There's still a lot of issues going on. So that's why I said it's an eternal question to ask. And there's no single causal model can explain all the relationship between causes and results. So it simply depends on the characteristic of the disease. But personally, I prefer to use the Rothman's sufficient, necessary, and contributing factors set. It will be useful for us to understand what's going on. And nowadays, the diseases are more and more complicated because of the research is more about chronic diseases. So generally, it's multiple factorial. So it's more Rothman model makes more sense in that way. And the guidelines for judging causal are not a checklist. So even if we find a specific research topic, check from the beginning to the end. Is this necessarily causal? No. But the more, the better. Okay? He's handsome, he's rich, he's humor, he understands me, but is he necessarily a nice husband? I'm not sure about that. Okay? But the more, the better, right? Weak risk factor could be a strong confounder if the relative risk is pretty small, like 1.2. But if the distribution differ a lot between the comparison groups, the effect could be very strong. So it really depends on how it is distributed in comparison groups. Some people said, I only control the confounders with a significance finding in a univariable analysis. No, it's not the right way to do it. Okay? So if it's essential, well-known, well-characterized risk factor, independent risk factor, then you should do it, no matter how small it is. Even if there's no significant statistical significance for gender, for example, or age, you still need to control it because everybody does it. So you have to do it, even if it doesn't change too much. Or it doesn't change your estimation of relative risk at all. Okay. And no risk factor is really independent to the others. So what I said in scenario insight of confounding or effect modifier is not definite. So that's why some factor could be considered as a confounder and also effect modifier. And don't adjust the confounder unless you are pretty sure that it's really an independent risk factor. So don't abuse the method I suggested in the stage of data collection and stage of the statistical analysis or data analysis. We only do it with well-known, well-characterized independent risk factors. Okay, read my lips. Confounder is a necessary evil, especially for observational study. Even if we perform the randomized controlled trial, we cannot get rid of it. It still happens by chance. So we simply assign them randomly, and eventually we find that the gender structure is different. Then we still need to do something to deal with it. So it's just like a friction in classical mechanics, in Newton's physics. It's like friction. So now if you want to invent or develop a new train system or new machine, you need to consider the issue about friction. If you want to build a tower or build a bridge, you still need to consider friction. So they're everywhere in engineering, right? So confounding is something like that. It's just a necessary evil. It's everywhere, so you need to deal with it. It's never been easy to control confounding perfectly, but it's possible to do it properly. That's the major thing you have to learn when you are trying to perform data analysis in epidemiology. Okay, so no matter what I'm going to teach you in a case control study, cohort study, or randomized control trial, this is the major thing we have to deal with. Age and gender are essential ones. It's very unlikely to find any health events not related to age and gender. The disaster for Hiroshima, Nagasaki might be an exception, right? It even happened in the Titanic disaster, right? Where the mortality is higher for young men and lower for children and women, right? Even something like a Titanic disaster, age and gender is still a very important risk factor for people to be drawn in a disaster. Okay, and don't abuse confounding control methods, please. You will learn a lot about it, but don't abuse it. Especially nowadays, computers are so available, it's so affordable, and the statistical software is there, and you could download it for free for R, right? But don't abuse it. Do it wisely, do it properly. That's very important in epidemiology. The last thing is about ways to think. In many clinical observations, we found that hospitalized patients experienced cardiopulmonary resuscitation, or CPR, were less likely to be discharged alive. In other words, if someone experienced the service of CPR, would be more likely to die. Right? That's very straightforward, right? Or intuitive, right? But is it true? CPR is killing people? Based on such a striking finding? Yeah, the relative risk is so high. Maybe 9. If someone were treated with CPR, then he or she will be more likely to discharge because he or she died in the period of hospitalization. If not, then why not? And the other analog is that if you are getting married and you find that the cousin of a fiancé is your true love, that's confounding. True love, X. But if your mother-in-law or father-in-law is a very difficult person to deal with, then that's effect modifier. Yeah, friction is so important, so that's why engineers are trying to develop something like a maglev train, right? To minimize friction, to save energy and also speed up the train to more than 500 kilometers per hour, right? Because then minimize the friction. So it's a kind of progress for technology, right? So in epidemiology, it's the same. We try to minimize the friction to enhance the comparability between the comparison groups. That's the essential thing. The tasks for epidemiologists. So can anyone tell me that? Is that true? Or there's something wrong with the conclusion? CPR is killing people in hospital or in the ER, emergency department. Yeah, he or she might be dead, or he or she is very close to death. Yeah, that's why they got a CPR. Yeah, so this is a typical phenomenon of confounding. We call it confounding by indication. What is the indication for CPR? The heart stop beating, right, or stop breathing. Okay, we have to clean the airway and try to push and blow, right? So that's how we can save people's life somehow. But how can we deal with it? How can we do something to make the result making more sense? It might not be a perfect suggestion that if we could assign the people when they need CPR, we send in 2 different groups. One group you do CPR and the other group you don't do it. Okay, so they're at the same level of severity in the very beginning, right? And we could compare what happened for their survival status, right? It makes more sense, right? Then what's the issue being considered? The severity of the vital sign, right? They have to be, the comparison group has to have the same or very similar vital sign or severity of the disease. Then we could make the conclusion. Right? It's like elephant in a room. Right? It's so apparent, but it happened. I mean, the mistake about confounding control happened everywhere in a lot of epidemiological studies, even if it's been published in the top journals. It happened a lot. So it's very important to learn how to consider confounding, how to control them properly at different stages. So that's the key point for the following lecture in epidemiology. Okay, I've spent so much time to build up the story about why we need to do the comparison, what is the indicator about the comparison, which is relative risk, right? And how we can make sure that they are comparable to each other, to have a better or more precise estimation of relative risk, to compare different groups, no matter it's exposure to non-exposure or the case to control groups with different kind of study design. So now finally we could step on into the details of different kinds of study design. That's the third stage of my teaching in epidemiology. The first one is like trigger your interest of epidemiology. And second bit is about relative risk estimation and confounding control. Third one is detail of different kind of study design. There are totally different kind of specific consideration for different kind of study design to make a better epidemiological studies. Okay, thank you. See you.